Now, before I get into the nitty-gritty, I have a kind of announcement to make, I suppose. In an earlier session, you may remember I was toying with the idea that I might give some special lectures sort of outside the course, not in the content of the textbook that we're using for this course, Sipser's textbook. So I made a decision of which text to use for these extra lectures, and you may remember the theme was essentially Gödel's incompleteness theorem, but and its links with Turing, because Turing, like the whole notion, if you think about it from a historical point of view, the computers that we live with today, I spend literally many hours every day on my computer, because I'm processing all this movie making. I film about an hour and a half, I guess, per day. So it's sort of relentless. So it involves quite a bit of processing time. I have to then download the raw film from the camera, the camcorder, to the computer, and then it goes through Microsoft's Movie Maker. For some reason, it enhances the quality, the readability of the text on the board, which is a good thing, but it's slow. And then I have to cut it up, and then I have to put titles in front, and then upload it to YouTube, which takes hours for just 10-12 minutes of film. Upload time typically about, if it's going well, about 2.5 hours, but often it'll crash or it'll stop, or contact with the VPN that I'm using to get around the censorship of the FG. You can guess what that stands for. Anyway, so I use my computer a lot, and so a lot of you. And where did this all come from? Well, it came out of Turing's work he's inspired by the ideas of Gödel, and Gödel himself was answering a challenge from Hilbert. And basically what Hilbert was, you see, around about a century ago, there are lots of mathematical paradoxes. I'll give you a taste just of one, to give you a feel for what was involved. But there were lots of mathematical paradoxes that created problems in the foundations of mathematics. A century ago, people were trying to codify mathematics, axiomatize math, so that it stood on a firm basis. But Bertrand Russell in Britain, he noticed that there were real problems, like paradoxes. You get I'll give you one. A small island, say in the Mediterranean somewhere, and all the men on this island, when it came to shaving, they had two options. They could either shave themselves, or if they didn't shave themselves, they went to the barber. And there was one barber on this little island, okay, just one barber. And then, it seems clear enough, okay? Except when you ask the very inconvenient question. Given this rule, all men either shave themselves, or they go to the barber to be shaved. Well, the inconvenient question is, well, who shaves the barber? Okay, and now if you use the rule that all men who do not shave themselves, the barber shaves them. Okay, so you come to two conclusions which are mutually contradictory, and there's you've got a paradox. So here it is. Okay, so assume the barber does not shave himself. Okay, and according to the rule, because the rule is all men who don't shave themselves go to the barber to be shaved. Okay, so this barber does not shave himself, therefore by the rule he goes to the barber to be shaved, and therefore the barber shaves the barber. Huh? But we just said before the barber does not shave himself. So in other words, if the barber does not shave himself, he does shave himself. Right? So contradiction. And let's say the barber does shave himself. Right? Then by the rule, he does not go to the barber to be shaved. Right? So the barber does not shave him. But who's the him? Well, the barber. Therefore, the barber does not shave the barber. So, and from that you conclude, so if the barber does shave the barber, therefore he does not shave the barber. Oh boy. Okay, so people were using sets to, using set theory as the basis for the foundations of mathematics, for arithmetic, arithmetic of whole numbers and so forth. And Russell, the same Russell, Bertrand Russell, and a colleague, Whitehead, they wrote tomes, really thick books on set theory to create the foundations of integer-based mathematics, the foundations of math, trying to avoid these paradoxes and so forth. And Gödel was reading this and had a flash, and that inspired him to create his famous incompleteness theorem. And then Turing in turn read this and was inspired by it, and also he tried to answer Hilbert. Now Hilbert, let's see, I think in the 20s, I'll be sure on the dates, I think it was in the 20s that Russell and Whitehead were publishing their tomes, these huge tomes, on the foundations of mathematics. Now, Hilbert, the German mathematician, he was stating earlier that his big challenge was to create a set of axioms such that all the statements that you could deduce from those axioms could be proved to be consistent. In other words, it would, given the axioms, given this set of axioms that were to be created, that was the challenge. The problem was to create these axioms, which would decide then whether a particular formula about properties of integers, whether that could be deduced from the axioms, and that there was no possible contradiction. So this set of axioms would deduce all possible statements, theorems, if you like, about integers, and this set of axioms could not, by its nature, generate two statements, and one would be the not, the contradiction of the other. Okay, that was his challenge, and so could these axioms decide whether a mathematical statement one of my motivations is to teaching this stuff is to be able to teach. I have to study it really well. So at the moment I'm still a bit scratchy, and that's my main motive for teaching it. And the other one is it's just so fascinating because Hilbert's challenge was find a set of axioms that would allow you to do what I just said, and make it would decide whether a given statement could be deduced from the set of axioms. And so this problem of creating these axioms and rules of inference was called the Entscheidung. It's a German word. Entscheiden in German just means decide. So Entscheidung is a decision. And Entscheidung Problem in German is just problem. So decision problem, if you translate that literally. Entscheidung Problem. So that was the challenge. And so Turing thought about this and started to think about how could you find a procedure, some method, some recipe, some step-by-step process that would allow you to make the decision whether a given statement could be derived without contradiction from the axioms. And out of that came the Turing machine. And we'll talk a lot about the Turing machine in this course. And the Turing machine, and with his notion of the Turing machine, and Turing machine is an automaton, so we're starting to head towards the concept of the Turing machine. And then from that he generalized it. He realized that it would be possible to make a machine that could simulate any other Turing machine. So it was a kind of universal Turing machine. And Turing machines get programmed. They have a kind of tape. I'm jumping ahead a bit, but we'll do this in detail in the course. So this tape instructs the Turing machine on how to calculate, how to make a decision on, it calculates in some vague sense. We'll do that later. So this universal Turing machine could simulate any Turing machine, performing some specific task. So in other words, a Turing machine became then a universal or general purpose Turing machine. And each Turing machine had its own tape that tells the Turing machine what to do. So it's